Hello, this is Professor Keene. In my last 4 lectures on Chapter 27 of A Student's Guide to the Great Physics texts, I've been talking about the development of Newton's universal law of gravitation. So I want to make some summary comments in this and the next lecture and work out some example problems, some of the implications of Newton's universal law of gravitation. So here we go. Newton's universal law of gravitation. That is the topic that we'll be discussing. This was developed by Newton in 1687. That was the first publication of his Principia. And it was developed, you might recall, by considering what type of force would be necessary in order to cause the planets to move in the way that they do. So that was what he did in his Principia. He didn't write the formula in the way that we do today. Remember, what we've done so far is we've said that Newton found that the force of gravity was proportional to 1 over the distance squared. That's what we got to in studying the Principia. Today, you will often see this law written in the following way. The force of gravity, that's force sub g, that means the gravitational force, is equal to, I'm just going to draw it out and I'll explain it. Capital G, m1, m2 over r squared. This is how you will often, in textbooks, see Newton's universal law of gravitation written. Notice it captures the fact that it's an inverse square law. So if we, for example, have a mass m1 right here and another mass m2 right here, and they are separated, the distances between the centers of them are separated by a distance r. That's the r that appears right here. So it's an inverse square law. As the distance gets farther, the force is weaker, but it also depends on the product of the two masses. So m1 and m2 are the masses of the two objects. So this might be, for example, the mass of the sun, and this might be the mass of the earth. Capital G, this is called the universal gravitational constant. It's a constant of nature as far as we know, kind of like the speed of light and the charge of an electron and the mass of an electron. It's a constant of nature, and it has a value in the MKS system of units of 6.67 about times 10 to the minus 11th newtons meters squared per kilogram squared. Okay, that is a numerical value of the universal gravitational constant. This value, by the way, was not measured by Newton. Of course, it couldn't have been because he didn't use the International System of Units, which consists of newtons, meters, and kilograms. But he didn't even measure what the value of this would be in some other system of units. It was measured, so G was first measured by a man named Henry Cavendish. Henry Cavendish in 1789. So this was almost 100 years after the time of Newton, using what's called a torsion balance. Torsion balance? What is a torsion balance? Well, for those of you who may have taken my Physics 202 course, you used a torsion balance in order to measure the force between two charged spheres. So what the torsion balance consists of is a thin steel wire or other metal wire with a little straw hanging from it, and on one end of the straw is a ball. On the other end is just a counterweight, like a little vane or something, like a little feather. So this is, imagine like an arrow hanging from a string with a mass on one end. And then there's another ball right here that's hooked up to a couple of straws that are fixed into a stand like this. And one can use this to measure the attractive or repulsive force between two objects. So in Physics 202, we charged these up with electrical charge and measured the force of repulsion between them by measuring how much the wire twists. Cavendish used a rendition of this to find the attraction between not two charged objects, but rather two lead balls. It's a very difficult measurement to do because the force is quite tiny for very small masses that you can have in a laboratory. In any case, this would be mass 1, this would be mass 2, and r would be the distance between the centers of these balls. And because g is so small and those masses are, a kilogram, the distance between them might be a centimeter or something, you'll get a very tiny force and a very small twisting of the wire. And by measuring the force as a function of the distance or as a function of the masses, one can determine what the gravitational constant is. Okay? By the way, the mathematical form of the universal law of gravitation looks very similar to Coulomb's law for electrical charges. So again, if some of you have taken electricity and magnetism course, you might recall that the force between two charged objects is equal to some constant called the Coulomb constant times the product of the two charges divided by the distance squared. So this was Coulomb's law. And Q are electrical charges. So the mathematical form, they're both inverse squared laws. They have different constants. This is universal gravitational constant. This is the Coulomb constant. And whereas Newton's law of gravity includes masses, this includes charges. Otherwise, they look remarkably the same. Okay. Notice that, as I mentioned, the force depends on the masses involved, mass 1 and mass 2. And because both of these masses are involved, this is a symmetric force. What do I mean by that? Well, mass 1 is pulling on mass 2, and you can compute the force, but mass 2 is also pulling on mass 1, and you can compute the force. The force of mass 1 pulling on mass 2 using gravity is equal to the force of mass 2 pulling on mass 1. Because both of those, the product of those masses, appear in this formula. So this automatically satisfies Newton's third law. Automatically satisfies Newton's third law that says for every force there's an equal and opposite force. Okay? And it doesn't matter what the sizes of these masses are. The force with which this one pulls on that one is exactly equal to and opposite in direction the force with which that one pulls on that one. And either one of these forces can be computed using the universal law of gravitation. Okay. Now, having said that the force of attraction depends not only on the distance but the masses, you might immediately ask, wait a minute, why, if the force of attraction depends on the mass of the object, then why do all objects here on Earth fall with the same acceleration? So here's a question. If the force of gravity depends on the masses involved, then why do all objects that are dropped, experience the same acceleration? After all, they should be experiencing different forces. If you drop a rock, a heavy rock like a block of lead, and you drop an apple, because the heavy rock or the piece of lead has a bigger mass than the apple, shouldn't it, by virtue of feeling a bigger force, experience a bigger acceleration? There seems to be something counterintuitive about this. So let me draw these two scenarios and explain why this would be the case. So I'm going to draw the Earth right here, and we'll have an apple right here. And the Earth has some mass, capital M, that's the mass of the Earth, and the apple has a mass of the apple. And let's suppose the center of the apple is some distance r from the center of the Earth. So I'll go like this. That's the distance of the apple from the center of the Earth. That's case 1. And case 2, we have the exact same Earth, but now we have this chunk of lead or some other heavy rock that has a different mass. We'll say the mass of the rock is over here. And suppose that it is the exact same distance from the center of the Earth, right? So the Earth's mass is the same in both cases, but there's a different mass here than here, and as a result, there will be a different force. That's the force acting on the apple, and this will be the force acting on the rock. Because in computing the force acting on the apple, we use this law of gravity, and in computing the force acting on the rock, we again use this law of gravity. And because they have different masses, one would anticipate a different force. So let's actually do that. Let's plug in these values. So what is the force acting on the apple? It is going to be equal to g times the mass of the apple times the mass of the Earth divided by the distance between the apple and the Earth squared. And what is the force acting on the rock? Well, that would be, once again, the gravitational constant, but now times the mass of the rock times the mass of the Earth over the distance squared. So because they have different masses, you'd anticipate a different force. The force on the rock is going to be large, the force on the apple is going to be small. So again, why, if they're feeling different forces, would one find that they fall with the same acceleration? After all, that is what Galileo had claimed, that all objects dropped in a vacuum, if you were to somehow get rid of the air, these two objects would fall with the exact same acceleration. How could this be? How is this consistent with Newton's universal law of gravitation? Well, let's go to Newton's second law. The force acting on the apple is going to be equal to the mass of the apple times the acceleration of the apple. And likewise, the force acting on the rock is going to cause that rock to accelerate. Okay? So I'm treating these cases separately in these columns. Now, this is Newton's second law right here, right? Now let's plug in what is the force acting on the apple? Well, we know it is just this gravitational force that is given by the universal law of gravity. And likewise, what is this force? It's a gravitational force given by Newton's universal law of gravity. So let's plug that in. So on the left-hand side, we have g times the mass of the apple times the mass of the Earth over r squared. That is equal to the mass of the apple times the acceleration of the apple. Acceleration of the apple. And likewise over here, we plug in the force of gravity, g times the mass of the rock times the mass of the Earth over r squared equals the mass of the rock times the acceleration of the rock. You might see where I'm going with this at this point. So this is the force, and this is the response to the force. This is the force, this is the response to the force. Notice that the mass of the apple appears here and here, so I can cancel those out. And so I find the acceleration of the apple is going to be g times whatever the mass of the Earth is divided by the distance from the Earth to the apple squared. And likewise over here, the mass of the rock cancels out. So the acceleration of the rock, once again, is g times the mass of the Earth over r squared. There we have it. Notice that they both of them experience the exact same acceleration. The acceleration of the apple is equal to the acceleration of the rock. It is because, although the force depends on the mass, the response to the force also depends on the mass in such a way that the masses cancel out and you get the exact same value for the acceleration. In fact, the acceleration that both feel, we call that a, it's equal to g times the mass of the Earth divided by the distance to the Earth squared. And if you plug in the value for g, the universal gravitational constant, and you plug in the mass of the Earth, and you plug in the distance from the center of the Earth to the surface of the Earth where we're doing this, you will find that this is about equal to 9.8 meters per second squared, which is what we call little g, the gravitational acceleration of gravity. We get that result by simply plugging in the gravitational constant, the mass of the Earth, and the distance from the object to the center of the Earth. Okay, so notice a couple of things here. First of all, if we were on a heavier planet, or rather a more massive planet like Jupiter or Saturn, and we're standing on the surface, there would be a different gravitational constant. I'm sorry, there'd be a same gravitational constant, there'd be a different acceleration of gravity, little g. Instead of 9.8 meters per second squared, it might be 10 or 20 or 30 meters per second squared. So it depends on the mass of the planet on which you are dropping the object. Secondly, notice that it depends on the distance from the center of the Earth. The value of g, 9.8, really only works when you're in a region right near the surface of the Earth. If you go up to the top of a mountain, several miles up, g is going to be slightly smaller because r is going to be bigger. And likewise, if you drill a hole and go toward the center of the Earth, then your distance from the center is going to be smaller and g is going to be bigger, for example. Okay? All right. I think that's all I want to say for now. Let me pick up the next question. I want to do a couple of examples when we get together next time or in my next lecture.